Okay, you guys ready? Sweet. How many of you were here on Tuesday? Okay, basically everyone. Sweet. So I was gonna do like a little bit of review back to the diode, just to cover like a new methodology on how to look at them throughout. And once we're done with that, we're gonna talk about MOSFETs in a little bit more detail, just to get your footing for when we go into the simulations. And then we're gonna go in the simulations, and then if we have time, I'll talk about filters once we're done with that. So. Oh yeah. No, you're good. Okay, is that better? Sweet. Yep. So that's kind of the, we'll see how it goes and then kind of readjust if needed. So first things first, can anyone give me like a succinct definition of a diode? Short definition. That's a good one. How about relay and the video that we played? Yep, yeah, exactly. That's what I was looking for. P-type and N-type sandwiched together, and then it forms a diode. So kind of going back to the first definition we heard, which is how the current flows within a diode. If we have a diode like this, how much current is going to flow? A lot. There you go. Okay. And now if we have a diode like this, how much current's going to flow? Little. There you go. Perfect. Okay. So now that we got that out of the way, if we have a voltage source, a sinusoidal voltage source, and we have a diode, and we draw out the voltage source and then we draw out, sorry, I'm going to modify the circuit a bit. Add a resistor in here, add the diode, and now we're going to look at V out here. What would the output look like on V out over time? Almost out of hand. Okay, that's okay. So to sections. So if we're looking at the positive half cycle here, and we draw it down to our next graph, and we're only looking at this section, our V out look like? Positive? Sorry, let me look at the MOS. It would actually be, since we're flowing, or sorry, instead of V out, let's look at I out. It's a little bit easier, especially since we talked about it that way in the last lecture. Okay, so in that case, yeah, we would have positive current. So I'm just gonna draw essentially what you would see. Note that there's like a little bit of a section here where there's no current, while their voltage is pretty low. And then again on the backhand, you're gonna have a section here where it's no current, when your voltage is pretty high. Or sorry, when it is also pretty low again. Um, then for the next section, when you're reverse biasing the diode, what would that section look like? Zero, exactly. I'll do this with a different color. And now you're coming back to basically the first half cycle again. What would it look like? Was that? Yeah, exactly. Yeah, you would see the exact same waveform again. Um, and this kind of methodology of time, then looking at another piece of time when the circuit changes effectively, and then like repeating that process is one way of doing analysis on these problems that makes it into like manageable chunks. When you're doing a half rectifier like this, it might seem like a little bit redundant, but when you pull out a few more devices, so let's say you have your same voltage source, but instead of one diode, you have four diodes arranged like this. Okay, so this is the second half of your first project. Um, does this like inherently make sense to anybody without talking about it? What's up?
You're just asking if it makes sense, and I was like, yeah.
Oh, okay.
Because if you were to follow, let's say, just say follow the electron on the positive half cycle, it will go through that top portion, go through the diode on the right, go back around, and then eventually just make its way back.
Oh,
And then, yeah, because I think those are backwards because it's supposed to go through the resistor first, go through the left diode, or the bottom left diode, then go back, and on the negative half cycle, they'll do the same thing except go through the bottom, that right diode, bottom right diode through the resistor, top left, and come back through the top.
yep. So you're saying this, right?
Yes.
Exactly. Yep. So if you were to take that and you were to draw it out, essentially doing the same thing that we were before with current IL on the y-axis, and then time on the x-axis. Essentially, what you're saying is for that first positive half cycle, your current would look essentially the same. Oops. Okay, and then for the negative half cycle, what would it look like?
It would be the exact same thing because it's able to pass through instead of just going through just the same diodes, but it'd be going through, let's say, the negative side through that bottom right, through the resistor, top left, and back to power supply.
Yep, exactly. So it looks something like that. And what you'll notice is that the current passes through the resistor in the exact same direction for the positive cycle and the negative cycle, which gives you something special, which is a second a second bump for both the positive and the negative half cycles. Um, and then the cycle repeats. Question?
Can you explain why it says square root instead of?
Yeah. This is with the assumption that the diodes are fully conducting or not fully conducting. It's a really simplified model. So you're right in that you would actually see something more like this. That's not supposed to be a triangle. Also not supposed to be a triangle. We're just gonna deal with my bad handwriting, I guess. Yeah, so it looked like two humps instead of two square waves. Yeah, so that's the second half of the project. Just to give you like some kind of way of approaching it. I think he covers it in class pretty well, but I had a couple of people come to the office hours last time and be like a little bit confused on how to break it up into different chunks. So I figured it would be worth talking about. Um, any more questions on this before we move on to basic MOSFET stuff? Yeah, of course. Let me just zoom out. Any other questions? Concerns? Thoughts? Okay, sweet. So really basic MOSFET stuff. I know last time I'd said that if you have a MOSFET and you're to put a positive voltage at the gate of that MOSFET, particularly an N-type MOSFET, then you'll flow current. And that still holds true. If you have a P-type MOSFET, they look pretty similar. The biggest difference, I think, is that you have an arrow that comes in the top instead of coming out the bottom. But from a functional perspective, if you have then you won't flow current. It's exactly the same logic as a N-type MOSFET. So if you have a negative, for argument's sake, then you'll flow current. But if you have 5 volts, then you won't flow current. I think he talks about P-type devices in the final, so this is like really far ahead. You don't have to worry about it too much. Just know that the logic's inverted. You won't even need this for the project. But now instead of just talking about like binary on or off, let's talk a little bit more about the voltage curves, which we like barely touched on last time. So if I'm gonna redraw this, and let's say the output of my voltage source here is gonna ramp over time. So it's gonna start out at 0 volts and then linearly increase to, let's say, 3 volts. If I'm looking at the current through the MOSFET, then this would look something along, hold on, let me change colors. Something along these. During the last lecture, I talked again very briefly about how we have this one section in the middle here that's pretty linear, and that's what we're looking for when we go and like first start a project with a MOSFET, is we want to know where that linear region is and how big it is, and from what voltage on the input to what voltage on the input it lasts, so to speak. Okay. So now that we have like some really basic MOSFET knowledge, we can start to like run simulations and stuff. Um, and yeah, I'm just gonna jump right into it, unless there's questions. Nope. Okay, sweet. Okay, so if we're gonna find that curve of our MOSFET, what would be the first step? We got a blank file.
Power supply.
Yep. Yeah, plenty of good answers. That's a great one. So out of power supply, we're also going to hold on, let me leave the call on my iPad. It's talking to me. Okay, there we go. Yep, so out of power supply, we're also going to need a MOSFET. You can go into the device library here and hit component and then just type in, I think it's just under, yeah, you can just click NMOS, then hit place. It'll pull up your MOSFET. And then we're going to add a few more things to this file. We're going to add a resistor. We're going to add a second power supply. And we can add a ground, but we can do that after we wire it. So I'm just going to go ahead and connect V2 here up to R1. Then I'm going to connect the bottom of R1 to the top of M1. Then I'm going to connect the bottom of M1 to the base of both of our power supplies. Once I'm done with that, I can connect the top of V1 to the gate of our MOSFET. And what this configuration allows us to do is we can modulate both the voltage at the top of the MOSFET, which dictates the amount of current that we flow through it, and it lets us modulate the voltage at the gate of the MOSFET, which also allows us to modulate how much current we flow through it, but by activating the device rather than just using Ohm's law. Yep. Oh yeah. So if you go up here, there's a little icon that kind of looks like a an op amp. Yeah, then you hit component. I think it's P. Yeah. I think you can also just hit M. Nah, it pulls up a wire. Yeah. So just hit P or click on that component at the top there. Then you go into search and you type in NMOS. And then it should come up on the component library. Yep. Okay, cool. And then from here, I'm going to go ahead and dictate the values of all of my components, starting with the resistor. I'm just going to right click it. I'm going to choose 1,000 ohms kind of arbitrarily. Then I'm going to come to my MOSFET. And we did place like a MOSFET, but unless we include a component like characteristic model with the visual model that we have, then it won't behave like we expect it to. So I'm going to click pick new MOSFET. It's going to pop up a list of a bunch of different MOSFETs here. I don't see a search functionality. I don't think there is on Mac either. We could choose something at the top. I'm gonna scroll a little bit to see if I can find a an N MOSFET, like a 1N by a different manufacturer. I'm not gonna see it, so I'm just gonna scroll back up to the top. And I'm gonna pick this first MOSFET. It's a 30 volt 2.4 milliohm MOSFET. That's pretty standard. Once you get up to the higher voltage ratings, they start acting a little bit non-ideal. So try to find one that has a VDS like 30-ish volts. All right, now once I'm done with that, I'm gonna set the voltage of my voltage 2. Just to make the math easy, I'll choose 10 volts. And then for the lower MOSFET, I'm going to do the voltage sweep through it. It doesn't matter as much what I choose for it, but I'm just going to go ahead and choose 1 volt. Then the last thing I need to do before I can start adding my spice command is add a ground. Oh, this is brutal. It's a remote desktop, so there's so much latency. Okay, I'm just gonna bite the bullet and wire it like that. Zoom out a little bit, zoom in a little bit. Okay, once I'm done with this, then I'll go ahead and add that spice directive. You can kind of write it by hand, or you can write anything down and then click on it and it'll let you use the GUI. So I'm just gonna write .dc, which is the start of the command. Then I'm gonna say which of the 2 voltage sources I want to target. In this case, I want to sweep the voltage going to the gate of the MOSFET. So I'm going to type in V1. I'm going to hit space again. I'm going to say what the lower bounds of the voltages I want to send to the gate to be. In this case, -1 volts is fine. Then I'm going to say the upper bound. I'm just going to choose 3. That seems pretty typical for most MOSFETs to be at the upper range of the gate voltage. Then I'm going to say the resolution. The smaller you make this number, the less coarse your graph is going to be. So I'm going to choose something a little bit small. If I choose, what is that? 100 microvolts per division, it should look pretty nice. And then I'm going to hit OK. Then I'm just going to place this at the bottom of my file somewhere. It doesn't matter so much. I'm going to hit save. Then I'm going to press run and then see if it's happy. Okay, it's going to try and include one of the other things I did earlier. That's okay. I'm going to hit run again. Much better. Okay. So the first thing I'm going to do is I'm going to plot the voltage at the gate of my MOSFET just by clicking on the wire. It's going to give me the line that I'm kind of expecting, which is around -1 volts. I know that's basically impossible for y'all to see. All the way up to around 3 volts. Then once I'm done with that, I'm gonna click on the current of the load resistor. Yeah, it's technically not the load resistor, but it kind of functions like it. And then it gives me the current of it, but it's really dark. So I'm gonna change the color of it from blue to a red. I do that just by right-clicking on the name of the current on the top right here. Pulls up a menu, gives me a little bar. I can change it from there. Yeah, in the Mac version of the software, I think you can also change the size of the lines, which is pretty nice. But here it doesn't let me. And I'm gonna look, and I'm gonna see that it's giving me some kind of ramp here, and then it just kind of goes off into space. which makes sense because we're looking at the current. If we minimize this, and instead we look at the voltage, which also I'm going to change the color to something a little bit brighter. And I think I'm going to delete the voltage source here. Or sorry, the current source. Okay, so it's looking like I didn't make the graph quite large enough. So what I'm going to do is I'm going to come back to my plot. I'm going to hop into the spice directive. I'm going to change the stop value to be 5 volts instead of 3 volts so we can see a little bit more of that graph. I'm going to hit play again. It's going to take a little while to load. And it's still not quite giving me what I want because it's going up, hitting some kind of plateau that's outside of our range, and then just falling off. Shoot, I think I deleted the wrong thing. Sorry, hold on. I'm gonna delete this. There we go. And I want the voltage of this. But it's still giving me the current. That's interesting. Okay, it popped up there for a second. See, sometimes it's a little bit finicky. You want to see this little red pencil looking thing. What that is it's like a really old-timey voltage probe. None of you will probably ever see one of these in real life because they're never used anymore. But basically it has like a little LED inside of it and you touch something and then if there's voltage there, it lights up so you can see it. But anyways, there we go. That looks a lot better. So now that we can actually see the voltage of the output, let me make it red so that shows up a little easier. You can see it kind of just drops like rocks. But at some point there should be a linear region. Let me go over to my other model real quick. Oh no, I don't have it anymore. Okay, that's fine. Basically, what we want is we want to avoid this little section down here where it's totally flat, and we want to avoid this section up here where it's highly nonlinear. So we're gonna shoot for the voltage of the gate in which it's mostly linear. So we're gonna be looking at this green line here. From 2 volts. No, that's too far. Sorry, maybe more like 2.5 volts up to 2.6 volts is like the only range where it's linear. It's kind of a weird MOSFET. Yeah, it's actually so weird. I'm gonna go and steal the MOSFET from my other model, which is the one I wanted to get in the first place. Sorry. I wonder if it's gonna let me. Nope, nope, nope. Okay, there we go. Nope, not gonna let me. Truly unfortunate. I wonder if it'll just let me copy paste the whole thing. Okay, I guess not. That's all right. We can just use this MOSFET. We're just gonna have a really, really small input voltage range, which will be kind of funky, but it should still work. So from here, we're gonna want to add, sorry, we're gonna want to take away the voltage that we got from the graph, and we're gonna want to input that into the bias resistors, which are the ones I were talking about yesterday. Um, if you connect them up just like you would without a MOSFET in the output of your voltage source, it should still work. But I'm just gonna add that MOSFET in for the sake of it. Okay, sorry. Delete that. Add the resistors in. I'm gonna add the capacitor in. Flip it. Okay, and this gives us the basic structure that we need in order to have a device that can be amplified or can amplify a sinusoid. So the sinusoid would be outputted from our V1. It would pass through C1, and then it would end up on the gate of our MOSFET with some amount of DC offset from R1, or sorry, from R3 and R2. And then the C1 prevents the current from V2 from entering back into V1. Just to make it simple, I'm going to choose like an arbitrarily small capacitance value. And the main thing that we need to focus on is our R2 and our R3 values. They dictate our voltage midpoint. So coming back to that graph, we don't have it anymore. Oh my God. I'm just gonna delete these real quick and then reform it, screenshot it, and then come back. Okay, there we go. So we got a voltage there, we got a voltage there. We want to see where they cross in the midpoint of the linear region, which is roughly right here, which is almost exactly 2.6 volts. And the way I'm looking at that is I'm literally just drawing a line in my head from 2.6 to roughly in the middle of this line. Don't pick this MOSFET. This MOSFET sucks. Typically this slope would be like, maybe instead of exactly vertical, it would be a little bit more like this. And it makes it a lot easier to eyeball it. I don't think we're gonna have a very smooth sinusoid with this thing, but that's okay. So instead of 2.6, maybe I'll scoot it back to like 2.59 volts. But before I do that, I'm gonna screenshot it so I can just reference it later. Okay, cool. I'm gonna come in here, delete that, put those things back. Okay, cool. So I want the bias to be something pretty exact, so I'm actually gonna have to do math instead of just like guess. So I'm gonna have to swap you over again real quick. I'm gonna stop sharing on there. I'll pull this up on my iPad. Okay, cool. Then I'm gonna join the Zoom call one more time. Okay, sweet. Okay, sweet. So if we redraw that circuit real quick over here, we're gonna end up with something that looks like this. Where our R2 is here, and our R3 is here, and then this will be our R1, and then this is our C. Okay. So this is 10 volts. We want the voltage at this node without the sinusoid doing anything to be almost exactly 2.58 volts. And in order to do that, what you do is you take this circuit, you strip everything away out of it that's not your DC components, and then you do V equals IR a couple of times. So to redraw it, I'm going to take that voltage source, it's 10 volts. I'm going to put my R2. I'm going to put my R3. And then I'm going to say this is 2.58 volts. And once I have this, I can kind of choose one of the two resistors arbitrarily. I mentioned last time that you want it to be in the tens of kiloohms in order to give it enough bias current, but not enough current to like waste power essentially. And I can't believe I went so long without explaining this. But MOSFETs don't have any current that enters the gate of it. So you reference this voltage here, but you have no current that flows into it. So this approximation works fine just because you have the capacitor on the left side, and you essentially have another capacitor on the right side that doesn't flow. So there's no current here, and there's no current here at DC, and therefore we can say this is valid. Does that make sense? Cool. So once I know the voltage, I'm going to choose R3 to be kind of arbitrarily 10 kiloohms because it makes the math a little bit easier. And once I know this voltage and I know the 10 kiloohms, then I can say use V equals IR. Say we have 2.58 volts at the node, and we're looking for I. So I'm going to take the R and I'm going to divide it over, but put it at the start. 2.55 or sorry, 10 kiloohms. Then you end up with 2.58 volts divided by 10 kiloohms. That'll give you the current through both resistors. Let me just do that real quick. 2.58 divided by 10,000 gives you 258 microamps. So I equals 258 microamps. And now we can find R2. So the way we find R2 is we take the voltage delta between the 10 volts, which is here, and the 2.58 volts, which is down below, and we just use Ohm's law again. So V equals IR. Voltage would be 10 minus 2.58 equals that same 258 microamps times R, which is what we're looking for. R2. So if we do 10 minus 2.58, we get 7.42. Divide that by 258 micro, and you get R2 to be 28,760. 28760. Normally I wouldn't be this accurate. I would just be like, okay, that's pretty much 28K or pretty much 30K, and I would go with it. But because this MOSFET is so steep, I have to choose something a little bit more accurate. In the real life, you'd be like, this MOSFET doesn't work for our design because I'm never gonna find a 28.76 kilo ohm resistor, and you find a new MOSFET. But because searching is difficult, I'm kind of ignoring that. Yeah. So we have our values for resistors, and we can hop back over the simulation software. So I'm gonna do the dance with the Zoom recording again. Okay. Projector's not happy. Okay, sweet. Cool. So we got R2, we got R3. I'm gonna say 28,760. And then on R3, I'm gonna say 10 kilo ohms. Just gonna save it. And then I'm gonna change this spice directive from being a DC sweep to being a transient. Notice I'm not doing AC analysis. AC analysis will give you a frequency sweep. So it'll go from whatever your start frequency is to whatever your end frequency is, and it'll give you a spectrum analysis result. And that looks weird and doesn't really help anybody for this application. You want a transient analysis. The transient analysis is your time domain analysis, and that's what we're looking for with the reports. So I'm gonna say stop time is 0.2 seconds. Data saving time is 0 seconds. Maximum time step, that's gonna be a resolution again. I'm gonna say 0001. External DC supply voltage at 0, that's fine. And it's not. Okay, there we go. I don't know where the input is for which voltage supply you're targeting. Oh, right, you don't need one, it's just transient. Okay, so I'm just gonna hit OK. Then I'm gonna modify voltage source here. I'm gonna go to advanced, which is gonna pull up the option to change it to a sinusoid. And I'm gonna do 0 voltage offset. I'm gonna make my amplitude the delta between those two values that we were talking about earlier, where the high was 2.6 and then the low was a little bit less than that. We're gonna have to tweak those values because it's so steep and it's so hard to see with the naked eye. So I'm just gonna say the amplitude is 0.02. And the frequency is 60 hertz. We're basically doing grid frequency here. I think it's the same for the projects. It might be 50 hertz. If you're in Japan or China, I think that's what they use. Oh, and the European Union, they also use that. Then I'm just gonna hit OK and then give it a try. And it is angry because I didn't define my capacitance voltage or my capacitance. So 0.0001. Okay. I'm gonna save again. Hit play. And it's looking at points which I'm not sure still exist. So I'm gonna delete those points. There we go. So this is their input. That was our input voltage. Oh, interesting. I think our capacitance value is too high. Nope. Okay, so what's happening is we biased slightly outside of the bias point of the MOSFET, and essentially it's always conducting, which is annoying. Oh, I'm just gonna delete this MOSFET and then try and find one that works.
You can right click on the part number.
Yeah? Oh, sweet. Okay, there's no undo button because I'm on the
You go to file or edit, there should be undo.
I'll do that next time. Thank you. Okay, you said right click on the part number?
Yeah.
It's not letting me just right click it, and it's not letting me type either.
When I did that, I had to right click the actual text right there where it says SI.
Where it says SI? Yeah.
And then right click I
Put on the actual
dash like part number.
SI7.
Oh, I see what you're saying. Okay, and then you just type in what 1N07 2N
70.
7002. Okay, sweet. Yep, that pulled it up. Thank you so much. Okay, so we're gonna have to do that biasing process over again. Shouldn't take nearly as long. So I'm gonna delete my capacitors. I'm gonna delete a couple of my lines, and I'm going to draw this one out, save it, play, and I'm gonna look at the point here. Looks good. I'm gonna look at the point here. Oh, that does not look good. I do not want a sinusoid anymore. I want a voltage sweep, and I want to change my transient back over to the DC sweep. Okay, cool. Try again. There we go. Okay, that's a lot better. You can see it's like a lot less steep, and you also have kind of a roll off at the bottom now instead of just a roll off at the top. If I make this transient a little bit more accurate, I think I can make that a little bit more pronounced as well. So if I hit 0 here, and instead of -1, I'm just going to start it at 0. And then instead of 5, I'm going to take it over to 3, just to zoom in essentially on the graph. I'm going to hit play. And yeah, it looks a little better. Maybe if I increase the resolution even a bit more, it would help, but it's just like the tiniest amount of the opposite end of that S curve now at the bottom. Yeah. Sweet. So now we can bias it. If we look in the middle here and we drag it straight down, it's basically exactly at 1.8. It's okay.
Why is the linear?
Yeah. I'll do an example at the end to kind of illustrate it in the shape of the sinusoid. But essentially, if we're going and we're injecting this green line into our MOSFET, and we go from, let's say, here to here, you can see that we're gonna have differing responses at different sections of that line. But if we keep it from, like, let's say this is 1.9 volts and this is 1.7 volts, and it's linear throughout that entire range, we can say if we increase our voltage by 0.1, then we'll increase, or in this case, decrease the output voltage by a linear amount. So let's say 10. So you just multiply the two, and then you can say that's your voltage gain, V over V. But if it's not linear, if that response isn't linear, then you would say for this portion, it would be 10. For this portion, it would be 20. At this portion, it would be 0.1. And you'd have to compensate for the lack of linearity with like controls, which gets messy. Yeah. And you would have to have a digital system, and yeah, we're just trying to do something analog here. Okay, so if we're centering it around 1.8 volts, which seems mostly okay. Maybe I'll do like 1.82 volts. We're gonna have to redo the math, which I'm just gonna do really fast here off screen. Shouldn't be that complicated. So 10 minus 1.82 volts. 1.82. So that gives us the I of 1.82 divided by 10 kilo ohms gives us 182 microamps. And then if we do 10 volts minus 1.82 volts, gives us 8.18, and divide that by 0.000182. Okay, that gives us basically 45 kilo ohms on the upper resistor. So we can leave the bottom one at 10 kilo ohms, and then we're gonna change the upper one to be yeah, 47 kilo ohms. The only other thing we need to do is we need to take a look at that graph again before we get rid of it. And we need to determine our upper and lower range. So it looks like our upper range of nonlinearity is like exactly at this point. So I'm going to zoom in again effectively. You can do that with the modeling here, but I think, yeah, okay, cool. File. Yeah, so you can do it with the modeling tool or you can resimulate it. Either one works. Cool. So 1.92, maybe 1.93 volts. And then you can see it's not truly linear, but let's call the bottom half 1.76 volts. So if we subtract 1.76 from 1.92, The delta is 0.16 volts. So we divide that by 2 and we get 0.08. So that's going to be the amount that we can have um, our sinusoid move. So that's our amplitude, 0.08 volts. C offset is 0, frequency is 60 hertz. And now we can start adding all that other stuff back in. Sorry, let me make it a little bigger for you guys. Go, add the resistors. Add the capacitor back in. All right, the bottom one is going to be 10 kilo ohms again. The top one is going to be 45 kilo ohms. Yeah, 45,000. Okay, cool. And then the it's going to be something small. All right, then I'm going to my spice directive to be back to the transient. I'm going to hit play. Okay, the system's unstable. I'm just going to delete this capacitor real quick, and then that should help things. Okay, it did. Incredible. Let me just move this about so you guys can see it a little bit better. All right, excellent. Oh my God, that took too long. I'm sorry. Yeah, we got a sinusoid on the output now. The blue line you can't see, but that's your input. And then the green line is your output. Ideally, on your paper, you would include these as two separate graphs because it becomes really difficult to read. But it doesn't super matter. You can just take this, and as long as I'm able to see both things, yeah, that is like totally okay with me. Another ideal thing is instead of showing like sinusoids like this, if you could just show like 3 or 4, something like this, it makes it a lot easier to read. And yeah, that's kind of the story. Casey, to like kind of elaborate on your question a little bit though, this is what it looks like if you have it biased correctly. If I were to change R2 to some arbitrarily smaller value, so let's say 2000, and then I try playing it again. Oh, it actually still looks pretty good. Hold on. Oh, sweet. Yeah. Okay. Not sure. Hold on. Let me make that 10,000 and I'm going to make the lower one a lower value. All right, it's just adjusting your voltage gain. I'm not sure why it's doing that. It should totally like change the shape of your output of your sinusoid. Let me just go back over to my other model here. I believe this is it, yeah. Okay, then if I hit play and then I measure the output, this is what it should look like if you change your bias resistors. And then if I'm going to tweak this again, to, I think this was at like, say 10,000. And hit it again, you can see it like changes the shape again. And then if you were to change it to a lower value, then it makes it a sinusoid. The reason for that is because, yeah, you're changing the point in which you're centering around that vertical section. Dude, I don't know for the life of me why the other model isn't working. It's exactly the same as this one, and I tried this before class and it worked great. Um, I apologize for that. But the other thing I wanted to show you is for the last section of project 2, they're going to ask you for how to get the THD. You do that by adding a second spice directive to your model. So you can do that just by clicking your spice directive, which is the darker dot T at the top. And then you're going to write dot 4, which is for your analysis. And then you're going to, sorry, one sec. I don't have it written down. Yeah, you're gonna write in for your analysis and sweet. Okay. Dot for your, then you're gonna do I think it's your desired frequency, and then from your desired frequency, you're gonna look at a couple of other values. Hold on. Wow, I'm not having it today. Yeah, you're gonna type in your frequency in hertz. Oh yeah, and then you target your specific output. So in this case, it's V out. So you type in V because you want to look at the voltage and not the current at that point. And then you type in a specific point. In this case, I labeled it V out. And then you can just hit play. Then you go to view and you go to this spice output log. Which if you get an error, all your errors also live here. In this case, we're just going to scroll down and we're going to see that we have about 5% total harmonic distortion. If you're doing a project and you want this to be lower, you can fiddle around with those bias resistors in order to try and get your device to be in a nicer location. They also suggest that you add a bypass capacitor for another resistor that would live here. But I think it's easier just to fiddle with the values of the resistors, R2 and R3, to get that to be lower. But yeah, let's go back to a little bit higher R2 in order to see what that would look like if you wanted it to be lower. File, view, log, scroll down, and now it's a little bit higher. You can see it's 8.1 when I do R2 as a 2500 instead of 2000. Have you guys taken 410 yet? No? Okay, that's the one where I think you learn Fourier analyses. It's basically just analyzing the frequency of your device by looking at it at different moments in time, I'm pretty sure. Which, if you're looking at a graph in the time domain, that manifests as that shape changing. The more wonky the shape is, the less sinusoidal it is. The higher that percentage is, the more sinusoidal it is, the lower that percentage is. If you're doing digital devices and you have switching noise on it, that'll lower your total harmonic distortion. Increase your total harmonic distortion percentage. If you're doing analog stuff, it basically just changes the shape instead of adding like a little bit of wiggle to it. Yeah, that's kind of like the majority of project 2. The last thing I wanted to cover, there's kind of 2 things. I wanted to show you how to source a component really quickly, because it's really something taught at the school at all, but it's really important. And then I wanted to have time. So there's really 2 tricks to finding components that work well. The first, which I'll show you in a second, is to filter by most purchased or most in stock on either DigiKey or Mauser. And the second is by looking at brand name, which you basically just have to memorize brand names. So the first one's way easier. So if I go onto Mauser, I think most people use DigiKey, so maybe I'll go on DigiKey. And I type in MOSFET. It's going to give you like a bunch of different options here. So it'll give you something that's not even a MOSFET. IGBT is a MOSFET and BJT in one package. It's going to give you modules. It's going to give you arrays. But what you really want is just discrete MOSFETs. In this case, they call them single MOSFETs. So you click on that. And now it's going to give you like a bunch of specifications that you can filter by. Most of the time, you're going to be looking for a MOSFET based off of 1 or 2 specifications, and you're not going to want to have to bother like filtering through all of this stuff. You're probably going to have a voltage specification, so your VDS. You might have some kind of current specification. So if you want to, you can add those in here. Otherwise, I normally just click in stock, hit apply. Because if they don't have it, why would I want to buy it? And then I go over here to quantity available. Once it does its thing. And I'm going to click the down arrow. So the very first thing, the very first things are all these devices that say marketplace underneath the stock total. Marketplace means that they have some other external suppliers that will ship it to them and then they'll then ship it to you. You don't want that. What you want is something that just says in stock. If it says in stock, then that means they have it in their warehouses and they can ship it out to you immediately. And you're probably just going to want to go for the device that's within your specifications and has the biggest number. I know that's like a drastic oversimplification, but if they manufacture 4.5 million of these things and they have 4.5 million in stock at any given time, generally speaking, it's a very general device. You can use it for a ton of different applications, and chances are your application is one of those applications. You don't have to nitpick every single detail, every single line item of the data sheet. A lot of the time you'll go and it'll feed you some random like Zener diode instead of a general purpose diode, and it's going to behave kind of funky, and you're going to be like, why is it doing this? And you're going to spend a ton of time debugging why it's a Zener diode and spend less time debugging your circuit as a whole. So this is like my general recommendation, especially if you go to senior design. This should be pretty helpful. Yeah, for this project, you're going to be looking for diodes. So let me pop open one of those real quick. If you want to do the extra credit, that is. Okay, there it goes. There we go. So again, we're going to go with single diodes. we're gonna go over here and we're gonna hit quantity available and go down. We're gonna scroll until we see something that says in stock instead of marketplace. Here we go. So this thing has 3.3 million of them in stock. And once we do that, we're gonna go and take the manufacturer part number and we're gonna find the spice model for it. So copy it, hit spice. It's gonna pop open the manufacturer page. And then it's right there on the right hand side for a spice model. You can find a lot of modeling within DigiKey itself using this bottom link here. But most of the time it won't have the spice model. It's just going to have the ECAD model, it's going to have the 3D model, and it's going to have the schematic symbol. But it won't have the spice model typically. So if I were to click that and I were to want to take this and put it into Altium or EasyEDA or something like that, that's where you find it. But if you want to do the extra credit, then you have to go to the manufacturer's page and then find it there. Yeah, any questions on like sourcing stuff? Nope. Okay, cool. Do you want to talk about filtering for 4 minutes or do you want to leave early? You want to leave? If you want to leave, raise your hand. Okay, if you want to talk about filtering, raise your hand. Okay, let's talk about filtering for 4 minutes then. Can anyone give me a really like quick 3-word explanation of what a filter is? Yeah, so that you're talking about a bandpass filter. Those are one of the more common, but also one of the more complicated types of filters. There's 3 types: low pass, high pass, and bandpass. Low pass filters are what you're going to want for these assignments, and they take your sinusoid or whatever, and it'll take those higher frequencies, even though it's only 60 hertz, and it'll let only a DC pass. Can anyone explain to me the simplest device that you can use to filter a signal? Yeah. Okay, there's one more. Let's say instead of voltage filtering, you want to filter current. Yeah, inductor. So I'm a power electronics engineer. I'm just going to draw a power electronics circuit because they're easy. If I have a diode and a MOSFET, and I'm looking at the output of this, and I'm going to have a square wave on the output of this if I don't do anything to it, and I want something, I can do a few things. I could add a capacitor. That'll make this look a whole lot better. It'll look kind of like, oh God, hold on. This goes down, and then goes down, and then goes down. It would look something like that. If I want to filter current, because let's assume I have some kind of load on the output of this, then I can also add an inductor. And then now you have like the most common output for a like a power electronic circuit. All you really need is a MOSFET, or sorry, a capacitor. You can do an LC filter here. So that means inductor and capacitor. If you're feeling fancy, inductors are expensive and they're complicated, and tuning them is kind of a pain. But in theory, if your load is big enough, you can filter with just an inductor. But we're looking at THD of voltage, not THD of current, so you're more better off going with, yeah, the capacitor. Cool. Any questions? Nope. Okay, sweet. That's it. Good luck.